The Unauthorized Guide to Using Spreadsheets in Chemical Engineering is an episode of the Degrees of Freedom project, videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. This video is an attempt to get you started on the techniques you will need to solve chemical and thermal process problems by using spreadsheets. In particular, we will be discussing how to lay out a spreadsheet to clearly convey information, how to enter formulas quickly and with a minimum of effort, how to use absolute and relative references, and in general, how to make things easier. The question arises, why spreadsheets? Well, first off, they are readily available. If you go into a typical office and look for a software, you're almost certain to find a spreadsheet program. LibreOffice is an open-source office suite that contains a spreadsheet module. It has most of the features of major commercial spreadsheets. While Google Sheets is also free to use, you have to deal with Google's terms of service, wherein they can look at any of your spreadsheets and use the information to assist their advertisers. It is also lacking some of the features that really help with chemical and thermal processing problems. We will work our example in LibreOffice. The tabular format of spreadsheets with columns and rows is an ideal match for the process flow diagram annotations, where you have a number of flow streams and each stream has a number of components. Perhaps the most important reason to use spreadsheets is that if you set up the spreadsheets correctly and don't embed problem parameters in the formulas, then you'll find it easy to correct errors and generate an updated solution with just a keystroke or two. In later videos, we will make extensive use of both GoalSeek, which is a numerical root finder, and Solver, which is a multivariate numerical optimization tool. One of the important things to consider when setting up a spreadsheet is formatting and layout. If you use a spreadsheet for professional purposes, you can get very fancy in your layouts. With a little extra effort and forethought, you can make a spreadsheet easy for a client to use. However, when learning spreadsheets, just make things clear, not fancy. Save the detailed formatting for after you've learned the basics. Just make sure that someone looking at your spreadsheet will be able to tell what your variables are and what it is you're trying to convey. Think about the layout of your spreadsheet from the end consumer's perspective. Where will the person who's going to use your spreadsheet look for information? Where do they expect to find things? How can you most clearly answer their questions? Label things in an obvious way. Group things in an obvious way. Put like things together and arrange them so that someone looking for information can find it easily. You'll want to code or mark your reference data, your input parameters, and your answers to distinguish them. The standard coding or marking we will use is green for problem or user input, blue for reference data, and bold for final answers. You could also use italics, bold italics, other colors, or other fonts to code or mark information. Properly format graphs with units on the axes. Include legends if there is more than one data series. You really want your graphs to look semi-professional and easy to interpret. To demonstrate many of the features of spreadsheets, we have a sample problem that reads, the chemical reaction, reactant A goes to product B, has been studied and has been found to be a first-order reaction. In a constant volume chemical reactor, that means if you start with a fixed initial concentration of reactant A, Ca0, in grams per liter, and no B, the concentration of B will evolve in time as Cb equals Ca0 times 1 minus e to the negative kt, where t is time in seconds and k is the rate constant or rate coefficient in units of per seconds. Your company hired 4 research labs to study the kinetics of the reaction at 5 different temperatures: 265 degrees Celsius, 270 degrees Celsius, 275 degrees Celsius, 280 degrees Celsius, and 285 degrees Celsius. The research labs have returned data tables that have the temperature, the initial concentration of A, and the measured concentration of B with the time. Like for all data, you should assume that there is some noise in the data. The attached spreadsheet contains all of the data and your technician has set it up with formatting to assist the data analysis. Your assignment is to plot the data, find the best value for the rate coefficient at each temperature, and determine the Arrhenius parameters for the data, so the company can use your analysis to design a chemical reactor. You also need to evaluate the quality of the data returned by the 4 labs. If you start with the equation for the concentration of B versus time, divide by Ca0, and isolate e to the negative kt, you get 1 minus Cb over Ca0 equals e to the negative kt. Taking the natural log of both sides yields ln of 1 minus Cb over Ca0 equals negative kt. So a plot of ln of 1 minus Cb over Ca0 would have a slope of negative k. The Arrhenius parameters are the A and E sub A, and k equals A e to the negative E sub A over RT, with T in absolute temperature. We can get at them by taking the natural log of the equation and plotting log k versus 1 over T. The slope is negative E sub A over R, and the intercept is log of A. We can multiply the slope by negative R, the gas constant, to get E sub A, and take the exponential of the intercept to get A. Here's a spreadsheet prepared by your technician. Let's fill it in. We have spaces for the value of k for each lab and for each temperature. We need to plot the log of 1 minus Cb over Ca0 versus T. The slope will be negative k. First, let's title each column as lm paren 1 minus Cb slash Ca0 paren and hit enter. We should leave it as is, but I can't resist changing B and A0 into subscripts. Click on the formula and select B, then choose Format Text Subscript. Repeat for A0. Now either drag fill to the right or copy the cell and paste it into the other cells. We'll now enter the formula. Equals ln paren 1 minus, and click on the value of CB in cell B7. Then type slash, and click on the cell for lab 1 CA0, cell B5. We want to be able to drag or copy and paste the cell to all of the remaining cells without having to change anything. So we'll hit the function key F4 and watch the dollar signs appear. A dollar sign means we always refer to the cell in this exact row or column, and no dollar sign means always refer to the cell in the same row or same column as this one. Since we always want the CA0 in row 5, we need a dollar sign in front of the 5 in B5, but we want the column to change as we change to the lab. So we don't want a dollar sign in the front of B. Press the F4 function key until there is a dollar sign in front of the 5, but not in front of the B. Twice usually does it. On some keyboards, you may need to hold down a key marked FN or something similar to make the F4 function key work. The pattern for repeated key presses, starting from no dollar signs, is both row and column, then just row, then just column, then neither row nor column. The pattern repeats. Once you've filled in the formula correctly, you can drag fill it right and then down. The graph for the data at 275 degrees Celsius should appear. You'll notice that there are two cells at 600 seconds for lab 2 and lab 4 that have an error message, error 502, in them. The cause is that if the measured CB is greater than or equal to CA0, then 1 minus CB over CA0 is negative, or 0. And when you take the natural log of it, you get an error. Since the measurements have some noise in them, the measured CB can be larger than CA0, even though the real CB can't be larger than CA0. The simplest way around the problem is just to delete the cells with errors in them. The better way is to use a different data analysis method, but that will have to wait for another video. Next, we'll find the slope and intercept of each plot. In the slope cell, enter equals slope paren, select the y values, comma, select the x values. We want the y values to change as we drag the cell to the right, so we put no absolute references in them, but we want the x values to stay in the same column as we drag to the right, so we press the F4 key 3 times to get the dollar signs in front of the a's. Then type a closing paren and hit return. Now drag fill the cells to the right. We have our slopes. Repeat the process for the intercept, except type intercept instead of slope. Why are we calculating the intercept? It's supposed to be 0, but with noisy data it will have some value. If the value is close to 0, we have confidence in our model. While we're here, let's calculate k. Enter equals negative, then click on k, cell F17, and hit return. No need for absolute references. We can select and drag all three, slope, intercept, and k, and drag fill right. The intercepts are all 1/20th or smaller, so we have confidence in our model. We need to choose the best value for k. Some sort of average of the k's would be appropriate, but lab 2's k and graph differ significantly from labs 1, 3, and 4. We're going to assume that lab 2 has a problem and leave it out of our average. Click on cell B18 and type equals average paren, then click on lab 1's k, cell F19, type comma, then click on lab 3's k, type comma, and then click on lab 4's k, type paren, and hit return. Did you notice that I clicked on the slope instead of the k? We'll fix that later. Repeat the process for standard deviation. The function we're using is stdev.s. The s stands for sample, which is what you use for sampled experimental data. The other choice is .p for population. Next, we will start on the set of data for 270 degrees Celsius. Select and copy the titles and first row of data from set 1 and paste it into set 2. Double-click on the first value for lab 1. You'll see the cells used to calculate it. The CB is pointing to the correct cell, but the CA0 is pointing to set 1. That's because we used an absolute reference for the row. To fix it, we'll drag the red box to the cell for set 2, lab 1, and hit return. It now points to the correct cell, and it now has the correct absolute reference for row 26. Drag fill left and then down. Since we set up the references correctly, we can copy and paste the formulas for slope, intercept, and k. You'll notice that lab 2 again is quite different from labs 1, 3, and 4. We'll again leave lab 2 out of our average. Now, since we let lab 2 out of the average standard deviation in set 1, and the references are correct, we can just copy and paste them into set 2. Oops, I just noticed the error with the best value for k. I'll fix it by double-clicking and dragging the cells from the slope to k. Now we can copy the best k and the standard deviation from set 1 to set 2. We need to repeat the process for sets 3, 4, and 5, but there's no point in doing so in the video, so we'll switch to a copy of the spreadsheet where those tasks have already been completed. Now we need to plot and regress the data for the Arrhenius parameters. Before we do, it appears that lab 2 has a systematic error in their recorded temperature. If their recorded temperatures are replaced with a temperature 14 degrees higher, their data makes a lot more sense. We were right to ignore them. You should let the box know. You see the columns for the temperatures in degrees Celsius and the k's as well as 1 over t and log of k. Click on the cell for the first temperature, Q4, and then type equals and click on the first temperature, cell B4, and hit return. Repeat for the second through fifth temperatures. Now repeat the process for the k's. Now we'll enter the formulas for 1 over t in inverse Kelvin. Click up the first cell, S4, and type equals 1/paren, then click on the first temperature and type plus 273.15 paren and hit return. Then drag fill the formula down. To enter the logs of k, click on cell T4 and type equals ln paren, and click on the first k, type paren and hit return. Then drag fill the formula down. The graph of log k versus 1 over t should appear. It looks pretty straight. To enter the formula for the slope, click on cell S9 and type equals slope paren, then select the ln k values, type comma, and then select the 1 over t values, type paren and hit return. Repeat the process for the intercept, except type intercept instead of slope. A sub a over r is the negative of the slope. Click cell S11, type equals negative, click on the slope, and hit return. To get E sub a, multiply by 8.314. If you're obsessive, you can type in 8.314, 4626, 1815, 324, but 8.314 should be fine for this exercise. Hit return. To get the value of a, click cell S13 and type equals exp paren, click on cell S10, type paren, and hit return. That completes this spreadsheet. You'll notice that the fitted slope and intercept on the graph are the same as those we calculated, if a bit excessive in sig figs. There are, of course, a lot more things that can be learned about spreadsheets in chemical engineering, and formatting can be much more complex than what we've taught. The takeaways from this video are: 1. With proper planning, you can arrange a spreadsheet to minimize formula entry and overall effort. 2. Think through absolute and relative references and lay out your spreadsheet so that you can use them to minimize the number of times you need to enter a formula. 3. Click filling and or copy once, paste many can really minimize your effort. 4. When starting out, don't worry about detailed formatting with superscripts, subscripts, special symbols, and italics. 5. Code your information with colors and bolding to make it easier for people using your spreadsheets to find the information they want. Thanks for watching. This video is brought to you by the DOFPro team.